Hi, this is Kerry McNamara at Bossier Parish Community College, and I'd like to work with you a little bit today on balancing chemical reactions, something that beginning students in chemistry find to be a challenge. I'd like to walk you through some steps here that I've found useful with students in the past and run through some examples of how to balance a chemical reaction. Now, a chemical reaction can really be thought of as a recipe. And with recipes, just like in the kitchen, we want to get the amounts correct for a recipe to taste good. So, with a chemical reaction, use that recipe analogy, and I'll use it as well as we go through this demonstration. One thing we need to follow, and you've probably heard this said in one setting or another in your science classes, is we need to obey what's called the law of conservation of matter. And all that really means is whatever goes into a chemical reaction or a recipe has to come out on the product side. So we have a certain amount of ingredients that go into a chemical reaction. The same amount need to come out in the products. Okay? That's obeying the law of conservation of matter. So let's take a chemical reaction as an example, a recipe if you will, and let's take some sodium for the first ingredient and some chlorine for the second ingredient, and the third ingredient will be some oxygen. And when we combine those together in the proper fashion, what we find we make is this product called potassium chlorate. Now we can see that the elements that go into a reaction, in this case potassium, chlorine, and oxygen, are the same elements that come out on the product side. If we had seen gold or silver or something else coming out on the product side that didn't go in on the reactant side, well, that's a different course. I don't know what course that is, but it's not chemistry. Whatever goes in must come out. What we can see, though, by just a cursory inspection here, is that the number of atoms of each element are not the same on both sides of the chemical reaction. For example, I see one potassium here and one potassium on the product side. That's actually okay. But two chlorine atoms on the reactant side, the ingredient side, and only one chlorine on the product side. And we can see a problem with the oxygen as well. What that means is that this reaction is unbalanced and needs to be balanced. So what we're going to do is make a list comparing both sides. We're just going to make a list of the elements that we see on the reactant side and the same list on the other side of the arrow in the same order of the products rather that we see on the right hand or product side. And you can do either side first, but we're just going to take a head count to begin with, counting the number of atoms that we see based on the formulas. So here I see just one potassium. Here I have a little 2 down below here indicating that there's 2 atoms of chlorine, and also a 2 by the oxygen down below indicating there's 2 atoms of oxygen. Let's compare that to the product side. We see in the formula 1 atom of potassium, 1 atom of chlorine, and 3 atoms of oxygen. So we see right away that this reaction doesn't match up. The numbers going in don't match the numbers coming out. This reaction is unbalanced. It's a fine reaction, but the recipe is not correct yet. We need needs a little bit of work, and we're going to go through that right now. Now, when balancing a chemical reaction, oftentimes I find students try to bite off more than they can chew at one time. In other words, they try to balance 2 or 3 elements at one time. I've found that the safest and most productive way is to go and take your time 1 element at a time. And reward yourself with little check marks, or I'll use smiley faces, when you get each element balanced. So we can see right away, potassium 1, potassium equals 1 on this side. Let's give ourselves, temporarily at least, a little smiley face here for the potassiums. Now that potassium was a metal element, and that's on the left-hand side of your periodic table. Metal elements tend to be the easiest to balance, and I recommend doing them first. Okay? In this case, there was only the one metal element, the potassium. It's good to have your periodic table handy to kind of set up which order you want to go in. The other 2 elements here, chlorine and oxygen, are both non-metals, and I recommend leaving them until the metals are balanced. And I really recommend leaving the oxygen till the end. You'll see that both in this reaction and a couple of the other examples we'll go through. So let's move on. Chlorines, we have 2 atoms of chlorine on the reactant or ingredient side and only 1 on the product side. There's a little invisible 1 written down below here. Well, one thing we're not allowed to do, which I've caught students doing in the past, is we can't go in and just, while no one's watching, make a little 2 there to balance the reaction. Okay, that's not allowed. The only thing we can do, and we have complete freedom in this case, is the numbers out in front. Notice I've put little blanks out in front of all of my ingredients and the product on the right-hand side. These are spaces for what are called coefficients. And if you've had an algebra class or any math class, you've probably worked with coefficients in the past. These are whole numbers usually out in front of letters x, y, z that multiply the amount of x, y, or z. And same thing here, except we're using, instead of x, y, z, let's say k, c, l, and o. Okay, so there's going to be some multiplication going on here. So getting back to our elements that are not balanced, the chlorine first, 2 chlorines on this side, 2 on this side, 1 on this side. The only way we can get that balanced is by putting a 2 out in front of the product. That 2 is placed there specifically for this element, but it also has a ripple effect. It's going to also multiply the potassium and the oxygen. But let's take things one at a time. We put the 2 here for this chlorine in the middle, of which there was 1 of. By putting the 2 here, we now double that and make 2, which matches what we had on the reactant side and earns us a little smiley face. But before we move on, let's update the other elements as well. That 2 also multiplied the potassium, so that's now 2. And guess what? That costs us this smiley face, at least temporarily. This 2 also multiplied the oxygen amount, so 2 times 3 gives us 6 oxygens. But they weren't balanced to begin with anyway, so no loss there. Okay. I hope you're using a pencil to do this because it's very much like a crossword puzzle. We need to sometimes go back and fix things that we've quote-unquote messed up. What we just did there by putting that 2 there for the chlorine is we unbalanced that potassium. The potassiums are now 2 on the product side and still only 1 over here. But on this side, we've got potassium all by itself. It's combining with chlorine and oxygen, but it's separated by this plus sign. So we can put any number we need to here, in this case, to get it up to 2. Let's put a 2 there. And that changes our potassiums to 2, and we earn back that smiley face. Okay? So 2 elements are now balanced. Now we look at the last remaining one, in this case the oxygen. We've got 2 oxygens still on the ingredient or reactant side. And remember, we have 6 from our 2 out in front before. To make 6 oxygens on this side, well, here's oxygen all by itself. And you'll find that elements all by themselves on either the reactant or the product side are real useful because we don't end up taking a step backwards by messing something else up. So to get this side up to 6 to match the product side, all we need to do, gang, is put a 3 right there. That 3 only affects the oxygen, makes 6 oxygens on the reactant side, and now you can see we have 2, 2, 6. 2, 2, 6, the reaction is now balanced, and just for closure, let's go ahead and put a 1 here. Okay, a blank usually means a 1, but I recommend students fill in any blanks with a 1. This is just 1 times 2, which keeps 2 chlorines there. So now the reaction is balanced. Okay? Notice one thing about this. In math classes, in addition, usually 2 plus 1 plus 3 equals 6. In chemistry, not so. 2 plus 1 plus 3 gives us 2 products, 2 what we call moles of product here. But if we go through atom by atom, we find that all the atoms that go in to our mixing bowl come out in our product, matching on both sides. Let's try another reaction. Let's take, in this case, C4H10, which is butane, combine it with oxygen, and we'll see the products that we get are carbon dioxide and hydrogen. Okay, and I'm going to assume that we're not balanced. We might be. Sometimes we get lucky and the reaction is balanced as written with all ones, but I don't think so in this case. So I'll put blanks out in front here again for coefficients. And to start off, let's just make a list of the elements we see on both sides and take a head count. So we've got on this side 4 carbon atoms, 10 hydrogen atoms, and 2 oxygen atoms. On the product side, let's do the same order, C, H, and O. And we've got 1 carbon. Let's see, the hydrogen's over here now, 2 hydrogens from the formula. And be careful with oxygen. Here we have 2 oxygen atoms, plus a 3rd on the water molecule, so we actually have a total of 3. Okay, oxygen shows up everywhere, so be careful with that. Okay, so we can see that none of the elements are balanced. All it takes is one to be out of balance in order for us to have to balance this reaction, any reaction. But we've got some work to do, it looks like. Now, in this reaction, we don't have any metals, so we can kind of forego that and go right to the non-metals, except, again, for hydrogen and oxygen. We'll get to them in time. The other element here is carbon. And on the reactant side, rather, we have 4 carbons going in on the reactant side, and only 1 coming out on the product side. Well, that's not balanced. Whatever goes in has to come out on the product side. So to balance the carbons, let's put a 4 in front here. And again, this 4 is distributed. Makes that 4. Makes oxygen. Let's see what we've got for oxygen now. 4 times 2 is 8, plus another 1 actually changes this up to 9. Okay, but that's okay. It wasn't balanced to begin with. The good news is the carbon is balanced. And for right now, we can, although there is an imaginary 1 at the moment, let's just put a 1 in front of that. Okay? 1 times 4 is 4. 4 times the invisible 1 here is 4 carbons. And let's proceed. Hydrogens. We've got 10 hydrogens on this side, lots of them, and only 2 over here on the product side. Well, we've got some work to do over on the product side in this case. To make 10 hydrogens, well, we find the hydrogen, and there's already 2 in the formula. What do we multiply 2 by to get 10? Let's try a 5 in front there, and that, again, gets distributed to both elements. Here, 5 times 2 actually gives us 10 hydrogens. And while we're at it, let's give ourselves a smiley face for 10 and 10. What does that 5 also affect, though? The oxygens. So let's recount the oxygens on this entire side. Okay, look everywhere for oxygen. Here we have 8 oxygens, 4 times 2, plus, that's 8, plus another 5 oxygens, so we're up to 13. Bad and getting worse on the oxygen. Okay, so we've got 2 elements balanced, carbon and hydrogen, and now we have the oxygen left to work with. Here's the good news. The oxygens over here, there's a lot of them, 13, and only 2 on this side. So it looks like the work we want to do is over here on the reactant side. And that's good because here's oxygen sitting all by its lonesome, not combined with any other element. In other words, any number we put out in front here is not going to upset any of the other elements that are already balanced. The problem is, though, when looking at 2 versus 13, there's no whole number, 13 being odd, that we can multiply this 2 by to make 13. But what we can do, and some students call this cheating, but it's not. If we get to the right answer, it's all good. If we put a 6 here, that would make 12. Close, but not good enough. If we put a 7 here, that would make 14, and we've kind of overshot the 13. But what's right between 6 and 7 is, of course, 6.5. 6.5, in other words. 6.5 times 2, and again, this is useful because this is not going to upset the carbon and the hydrogen. 6.5 times 2 actually gives us that 13. And that earns us a smiley face there. And again, my students say, I didn't know you could do that. Well, we can do anything we want when we're learning. But they're right. We can't leave that half there. Okay, we're supposed to have all what we call whole number coefficients, like a 1 or a 4 or a 5. This 6.5 really can't stay there. But we can fix this by just going to our call it our chemistry garage, and pulling out what I call our number 2 steamroller. This is my image of a steamroller. And number 2 really should be written as multiply by 2. What I'm going to do with this steamroller is just go through all my numbers in blue up here and multiply them by the factor of 2. Now if I do the same thing to every blue number, we're still going to be balanced. We're just going to be getting rid of this half number and getting whole numbers. So let's do that. If we multiply 1 by 2, we get 2. And if we multiply 6.5 by 2, we get 13. 4 by 2, we get 8. And 5 times 2 gives us 10. So the numbers we want for our coefficients in the end for this reaction are 2, 13, 8, and 10. Again, they don't add up to the same numbers on both sides, but what it does do is balance element by element, atom for atom, our reactants with products. Okay? Let's try one more. Again, one element at a time is the preferred way to go. And we'll keep that number 2 steamroller running just in case we need it again. Okay, let's take this reaction. Magnesium nitride, and we'll combine that with chlorine, and what we're going to get for product here is magnesium chloride and nitrogen gas. Okay, and we'll put our numbers out in front, or our spaces out in front for our coefficients, just in case we're not balanced. Okay, well, we might be balanced to begin with. Let's take a look and see. Let's make a list. Over here on the reactant side, the ingredient side, I see the element magnesium, I see the element nitrogen, and I see the element chlorine. And let's get a head count, see where we stand on this side. 3 magnesium atoms, 2 nitrogen atoms, and 2 chlorine atoms. On the product side, and again, try to go in the same order, even though they may have scrambled up their order, magnesium, nitrogen, and chlorine. And here I have, in this formula, only 1 magnesium. On this side I have 2 nitrogens and 2 chlorines. So what do we got here? Well, we're close, but close isn't good enough. The nitrogens and the chlorines are balanced, 2 and 2 and 2 and 2, but the magnesium is not. We've got 3 on this side and only 1 on the product side. Okay, well, magnesium is where we would start anyways, being a metal. So let's go ahead and try to get that magnesium balance to begin with. 3 on the reactant side, only 1 on the product side. Let's go ahead and put a 3 out in front here, and again that 3 gets distributed to both elements. What we put it there for was to do this, to get ourselves, at least temporarily, a balanced amount of magnesium on both sides, but that 3 here also changes the amount of chlorine. So we go from 2 to 6 chlorines. Okay. Let's take the next element that's not balanced. Again, the nitrogens are still balanced. They may or may not stay that way. Now we've got 6 chlorines over on this side and only 2 on this side, so that needs a little bit of work. This is the side with fewer, so this is the side we really want to try to boost up. And since chlorine, again, is all by itself here, kind of with a partner, 2 Cls, 2 chlorines, but if we put a 3 here, gang, 3 times 2 gives us 6. And now if we look at our numbers, we have 3, 2, 6, and 3, 2, 6. Any blanks that are left, just fill in with 1s. And now we have a balanced reaction. In this case, you'll notice, just by coincidence, 1 and 3 does actually equal 3 and 1, but don't look for that all the time. The numbers you do need to match up are the elements in each element on both sides, atom for atom. And again, that's done using coefficients out in front through some multiplication and addition.